Hi, everybody. I hope you all had an excellent weekend. Exam not included in that, although I hope you had an excellent exam. Um, for this week, I have to change the schedule just a little bit because I cannot keep up with the pace that I put out for myself. So, let's talk about the schedule changes, and then we'll talk about the exam because I have the scores in front of me, more or less. I can't compile them all together, unfortunately, but I can talk a little bit about them. Anyway, first of all, schedule changes for this week. Everything is down at the bottom in the announcement, so you can see it there. Worksheet number 3 is still due on Thursday, so that has not changed. Make sure that you get that in by the deadline so I can grade it this week. Lab number 4. I have been working on lab number 4 for probably 5 or 6 hours at this point, and I'm not even done with half of it because it is an Excel exercise. I should say Google Sheets. It used to be an Excel exercise. It is a Google Sheets exercise that requires me to write as detailed directions as I can because I won't be hovering over your shoulder to debug any issues that you have. And I realize that if I'm trying to teach students how to use Google Sheets or Excel in an experiment, I have to basically give you a bunch of examples and a bunch of, like, if you got this, you made a mistake, and then show you how to fix it. So writing the documentation for lab number 4 is taking way longer than I expected. And as a result, that lab's not done yet. So I won't likely have that finished tonight. So I'm going to make the executive decision to postpone the lab for a week. Next week we had no lab anyway. I'm going to make that this week just because I need to. So there won't be a new lab this week. There won't be a lab Q&A tomorrow or any sort of office hour because we just had an exam. There's not really anything to cover. But yeah, I will still be available by email. And if you need to ask me questions about anything related to lab number 3 or things like that, you can just send me an email and I will answer it that day. Okay. But again, no lab lecture. I'm not even going to post a link. I will post an announcement saying, remember that there's no lab this week. There are some questions about the Google Sheets for lab 3. Let's see here. So I did not have very many problems with people submitting Excel files and formatting issues last time. If your data is there and the graph is on your screen, and then you save as an XLSX file and then don't open it, just send it to me, and when I open it, it should be fine. I've had I would say like a 95% success rate on people sending me stuff, just downloading it from Excel. I think the important thing is you don't want to open it. Because if you open it, then your version of Excel will try and make changes and figure out what the formatting is. And that could move stuff around. And if you don't notice something is moved around and then you just close it and save it on accident, when I get it, then it might be removed or something like that. Yeah. So it might do some funky stuff, but I know that people were mentioning that for the first lab where you had to make a graph, and then when I got their files, everything was fine for the most part. So if you see the graph on your Google Sheet and you save the file, yeah, Schrodinger's Excel sheets. That's exactly what's going on. Yeah, if you did that, so download it and then just upload it, and it should be okay. And if it's not okay, I'll send you an email. I'm not going to be like, hey, your sheet is no good. Yeah, re-upload an unopened version. As long as you didn't open it and then hit save, because I know that when I open the gradebook, what happens is it asks me to save even though I've done nothing. And so I think Excel might just be trying to compute all the formulas. Try a bunch of things, and if it doesn't work, we have a whole week to figure it out because I'm not giving you another lab this week. So it should be okay. Next week's lab is going to be more complicated in the sense that you are going to build a bunch of formulas. And I will, when I go over the lab lecture for that next week, not tomorrow, like I said, I will show you how I want you to do it. And so we'll all do the assignment just only using, not Excel, but Google Sheets. And I know some people are like, oh, I have OpenOffice, I'll just use that instead and then export it. And so far that hasn't been awful, but there have been some weird issues with some reports where, like, all of the blue boxes that I get end up being, like, yellow or something weird because the palette is different. Okay, so that's labs out of the way. Let me know if you have any questions about that. I will make an announcement about all of the stuff that I just said after class today. I meant to do it last night, but I was just too tired. Let's talk about exam number 1. So I have the histogram for one of the two of the 3 sections, I should say. And it looks pretty good. Yeah, too tired, I know. You guys don't know what that means, I'm sure. You're students. No, everybody's too tired. So I have the histogram for 2 of the 3 classes. I can't get them all together because Canvas doesn't combine all this stuff. I could just plot the data, but I don't have it available. And it looks like the average was around 75 or so % on the exam, which is exactly where I want it. So that's good. I don't really have much to say about the exam other than due to some issues on Canvas, I have to change what your score is represented as right now. So Canvas wanted me to put a point value in for the exam, so I typed in 75. Then it wanted me to put in a point value for how many points the quiz was, so I put 83, and I told it just compute points. So, of course, Canvas computes it as a percentage, and then imports the percent, and is like, oh, you got 80% of the 83 points, so we'll give you that 80% out of 75, which is totally wrong. So I had to go back and edit it, because Canvas... I'm rolling my eyes, but you can't tell. So the score that you currently have displayed for your exam is wrong. I will go and fix that once I have all the exams in. I know a few people had to use their NQA coupon to take the exam today. Yeah, so your exam scores will be edited. It will be higher than what you see. And again, remember that I only take the higher of your 2 scores. And it looked like a lot of people did pretty good. Now, that 75% average that I quoted has all of the first attempts in there. So, like, I just have a bunch of attempts. And I'm only going to keep the highest of those. So, I am cherry picking from the distribution plot that I saw. As far as what do you do with your exam other than your grade, that's it. You don't get to see your exam again. You do not get to see the questions. You will not get to see which questions you got right. It's an exam, kind of like how a standardized exam, you don't get to see it ever again. That's more or less what I'm doing with this. The reason for that being, I do not want this exam to be posted all over the internet or Course Hero or whatever, because it took me all day to build it, and I'm not building it again. And also, you've only seen like one version of the 20 versions of the test anyway, so it doesn't really help me to go over it. And a lot of the questions were very similar in content, or even the same questions that you saw in the quiz. So, remember, you can always review your quiz for questions, but you will not be seeing your results on the exam other than the score that you got. I believe that is everything that I wanted to go over. So I can get rid of this. I do want this window still open. And yeah, there we go. Okay. So let's go here. This is where we left off last time. We were talking about quantum mechanics and how electrons behave. Actually, let me go back to the previous slide here. So we finalized our discussion of what quantum mechanics is as basically just probability. And so if I were to draw a classical path, I would just have this arced line right here that would say, oh, okay, here's my baseball I threw. It went along this path. But if I throw an electron instead, it could be anywhere along this path, but we don't actually know where it is. And due to the Heisenberg uncertainty principle, we don't know specifically where it is and which direction it's heading and its velocity and things like that. We could identify one of those properties at a time, and that's actually what this graph has done, is it's basically a ping map of, hey, where was the electron? And so anytime that it was found, then a dot was placed on this little arc. And you'll see that most likely the electron will be found on like the midpoint of this curve. But on the outside, which is very far from the curve, the electron is also likely to be found. So what this means is that we can't write orbits for electrons. And that's where the term orbital... Oh my goodness. I swear I fixed this, but I don't know why it keeps coming back. This is where the term orbital comes from. So this right here is an orbital, whereas a very predictable path would be an orbit. So, for instance, the Earth orbits the Sun, but electrons live in orbitals around the nucleus of an atom. And that is just a consequence of quantum mechanics. Alright, so that's a summary of what we went over last time. Today, we're going to learn how to describe orbitals. And the way that we're going to do that is we're going to assign them basically an address. And the address is going to be constructed from a bunch of different quantum numbers, one of which you already know. It's the principal quantum number n. And n represents the energy level of the electron, or in other words, roughly how far away from the nucleus it is. These are the 4 quantum numbers. We're going to talk about them one at a time. This first one that you already know is the first part of the address, and it's, in other words, the least specific component. For instance, if I was writing a letter, I know who does that anymore, and I had to write the address on an envelope. First you write their name, then you write the street address that they're in, and then you write the city, and then you write the state, and a zip code. Those get progressively less and less, what's the word that I want to use for this? Specific. There we go. They get less and less specific. For example, if I addressed a letter to Washington, like, that doesn't help anybody. Okay, it's got to the right corner of America, but now what do I do with it? If I address it to a specific person, however, that tells me who the letter should go to, and it would eventually find its way. So these 4 quantum numbers are going to proceed in an order of, this first one is going to be the least specific, and then this will be more specific, and this is more specific still, and this is the individual. So you could think of the first one as, say, like the city, this is the street, this is the name, this is the number of the apartment or whatever, and then this is who lives there. All right. On the right of your screen here, what I have drawn is an energy diagram, and I've put something at the bottom down here, and you'll see it right there. Whenever we draw these diagrams, excuse me, we draw them relative to the nucleus. The nucleus is always at the bottom of the diagram, and any electrons that are in the diagram, wherever they are attracted down to the nucleus, because the nucleus has a positive charge. And so this guy is attracted down too. And what we're going to have here on this energy diagram is a series of rows that represent each of the quantum numbers. And that's going to go all the way up to infinity here. So n has to be an integer for 1. In fact, we've only dealt with the integer n so far, and it turns out that that is required. It has to be positive, so it can't be 0. And any number up till infinity is valid. Now, the higher in energy your n is, so higher values of n go up the scale. And so what that means is that this is the lowest part of our energy scale, but it's not 0. In fact, what we're going to do is we're going to put 0 up here. And so this y-axis, I got to do it this way. our energy starts at 0 up here, but you'll notice I put the arrow up here. So this is going to have more and more negative numbers. So, for example, I might just call this one like -2, and this one might be -5. And I don't know, maybe this one's -20. And the reason that we have the scale decreasing like this is so that it makes sense when we use math to describe what's going on. So, for example, we discussed in section 3.2 that if you did this, and you take your electron and you move it up here, I gotta get the right color out, so now it's up here. In order to do this action that's written with the thick blue pen, you have to add energy. How much energy would you be adding? Well, if it started on -5 and it ended on -2, you could say that delta E would be -2, which is the final energy, minus -5, which is the initial energy. Or this much energy was added. So since I added energy to get my stuff to go up, I should have a more positive number, which is why we have all of these numbers written in the negative scale. And they get more negative as you go down. Each of these n values will have its own energy, and we can calculate that using some formulas. Oops, I didn't mean to reveal that yet. In the laboratory, you are actually going to calculate these, and we'll talk about that in more detail when we do lab number 4. But for now, this is just how the energy scale is set up. 0 energy is at the n equals infinity point. What does that mean? We'll talk about it when we talk about ionization. And the difference between NHU levels can be then calculated, which will correspond to how much light comes out. All right. Now, some other terms that we're going to use for these levels. So this n equals 1, n equals 2, etc. So you might hear the term shell or shell number. You might hear the term level. There's a bunch of different ways that this jargon is used in quantum mechanics. Most commonly, I'm just going to say it's an energy level, but you may hear the term shell to refer to the fact that the electrons that live in that level form a sort of shell of electrons around the nucleus. Because as we fill up energy levels, we're going to have to go to the next one. And as we fill that one, we'll go to the next one, and so on. And what we end up making is an atom that has a bunch of electrons around it, kind of like the skin on an onion. You peel away one layer of skin, and there's another one below it. You peel away that, there's another layer below that one, too. And with the atom, it's the same way. There's a layer of electrons, and under that is another layer of electrons, and under that, and so on. All right, so that's n. That's the principal quantum number n. The next quantum number we're going to determine is called L. L is the angular momentum quantum number, and by itself, that name doesn't really mean anything. And all we really care about is that the L value determines the shape. And we'll talk about shape later. Because the shape of an orbital is actually a complex mathematical model. And for our purposes, we don't really care about how that model is calculated, other than what is the output, because we're going to care about what the shapes are for Chapter 5. But for now, we don't really need to know that. What we do need to know is, how do we determine the value of L? N is very easy. You just pick a number, and that's what level you live on. But L depends on N. And the values of L that we allow are 0, which is the first number, all the way up through n minus 1. And I believe that that will pop up here. There we go. That's what I want. So for any given n, you can have a subset of values for L. which means that the bigger your n is, the more shapes you have. And in a way, this should make a little bit of sense, because if you have a very tiny n, your atom is going to be very small, and it's hard to fit very many shapes inside this tiny region. But if you have a big n, you can put many shapes in this region because it's bigger. And those shapes will have a specific volume to them. I didn't mean to erase everything, darn it. Alright, well, this is going to pop up in a second here, so we'll just do this. So the values of L are 0, 2, and minus 1, and they must be integers. Lastly, for what L means in terms of jargon or lexicon, we care about the term subshell, which means basically part of the shell of electrons, or sublevel. In other words, we're going to take our n region, and we're going to split it into different subregions. And those subregions will have their own shape associated with them. And the electrons will be restricted to being within that shape, because the shape will be our orbital. I didn't realize I typed it there, so I guess I could just erase this. There you go. Now, only specific values of L are allowed for a given value of n. So what we're going to do is we're going to do an example here. And I'll just put this on the screen here. And we're going to show how to calculate these quantum numbers. So for instance, if I say n equals 1, then I have to determine all the possible values of L. And so in the chat, what I want you to do is type out all the values of L that are satisfied for n equals 1. Remember, you're only allowed to have integers. And in this case, 0 is an integer. And there you go. So we can do basic algebra, right? So if n is 1, n minus 1 is 0. 0 must be less than or equal to L, which must be greater than or equal to L. And this is the only value that's possible. Okay, let's do n equals 2. What are the possible values of L for n equals 2? Type them in the chat. There you go, that's exactly right. Now try and type in the chat all the possible values of L for n equals 38. And obviously you don't have to type in every number, but like what would the first number be in the last number? Perfect, there you go, so you got it. So L equals 0, 1, 2, oops. All the way up to 37. So there you go, that's how we calculate L. And for each of these values of L, we're going to have a different shape. So for n equals 1, there's going to be one shape associated with n equals 0. Or I'm sorry, L equals 0. For n equals 2, I'm going to have two shapes. And for n equals 38, I'm going to have 38 shapes. Now, for the purposes of this class, we're only ever going to go up to like n equals, say, 7 or so. And the reason for that is because that's as many elements as that we have. It goes up to n equals 7, and then we don't have any other known elements past that. But all the n values exist, and so we could theoretically calculate their orbitals. All right, let's talk about the last quantum number that defines the orbital, because the very last quantum number is just which electron. And so that's m sub s. Oh, we already did this. Oh, we'll talk about m sub s in just a second. Or m sub l, whatever number I'm on. For each of these shapes of L, we're going to take the number of L, and we're going to turn it in. So is the number of L values the same as the number of shapes? Yes, that's correct, because each number value of L represents a given shape. And so these shapes are going to have letter codes assigned to them. And I'm showing these on the board here. And if this sounds completely outlandish and stupid to you, that's because it is. This is a model. This is what chemists have decided is the method that they want to use to describe electrons. And it does work, but it's really obtuse. And so what we do is we say, okay, whenever L equals 0, we're going to call that an s orbital. Whenever L equals 1, we'll call it a p orbital. L equals 2 is d. L equals 3 is f. And this keeps going. So whatever L is, we just keep going through the alphabet. Although I think that we skip vowels for some reason. And if you're wondering what S, P, D, and F stand for, it's really dumb. In fact, I will put the letters on the board here. So it turns out that when somebody was looking at a graph or a line spectrum, what they saw were sharp lines, they saw principal lines, they saw diffuse lines, and they saw fine lines. And so that's what S, P, D, and F stand for. Which makes no sense because what the fuck does principal mean? I can understand sharp. I can understand diffuse, but like, how do you differentiate between diffuse and fine? Like, it's stupid, so... It's stupid and chemists should feel stupid. For our purposes, it's essentially just random letters, and then after D, it starts going alphabetical. So there actually is another one after this. So you could do L equals 4, and it is called the G orbital. However, no electrons populate a G orbital in the ground state because we don't have an atom that actually does that yet. The first atom that would do that would be element 121, which has not been synthesized yet. So that's okay. But more important to each of these letters is they're going to correspond to a shape. So for example, S is going to be a sphere. And I'll show these shapes later. P is going to be kind of a dumbbell or sort of bow tie. D is just confusing. And really what the F stands for is the F in what the fuck. Because these shapes are just... I just can't draw them. Like it's ridiculously complicated. It's basically the D orbital, about two of them, and one is superimposed on top of the other. So we're going to assign shapes to these letters, and the letters are going to be assigned to various quantum numbers values for L. I got to erase this because I'm going to use the space. So when we determine the address of our electron by writing out its quantum numbers, we're going to take those numbers, translate them into letter codes, which is what this is right here, and then we'll translate the letter code into an actual shape. Clear as mud, I'm sure. But as we do this, it will become more intuitive. All right. The third quantum number is the magnetic quantum number, and it is basically just which direction your shape is pointing. Oops, I want to highlight right here. Yeah, that's really all I care about. I guess I highlight the word orientation. For different shapes, different orientations in space are possible because the symmetry of those orbitals is not necessarily the same around all three axes. So, for instance, and this is getting a little outside the scope of this class, but that's okay. If I have a coordinate axis in 3 dimensions, x, y, z, and I have a sphere like this, a sphere is radially symmetric around the origin, which means that no way that I can rotate this coordinate set will result in something that looks different. It will always just be this sphere. Oops, I didn't mean to erase that. So there's only one way to orient the sphere. But if I had one of those bow tie things, then if I rotated it on its side, I could go along a different axis. And if I rotated that one in the different direction along the other axis, I could go along a different axis still. And so for a bunch of these different shapes that we're going to draw out, there are different orientations that will superimpose with each other. And this just happens to be a consequence of how the math works out. I'm going to use that in scare quotes, the math, because in reality, when we calculate these shapes, the formula is very, very complex. And I will show you that formula just a little bit later. Why did that happen? There we go. I'll show you that formula a little bit later, and you'll see why we're not doing these calculations. All right. So the subscript is a lowercase l. Yeah, I wish that this font was a little bit more obvious, but it's not. Now, what values of m sub l are possible? Just like before, the range is going to be restricted based on the previous quantum number. So for m sub l, the values that we allow are negative L to positive L. I believe that appears on the screen right there. There you go. Now, what that means is that based on a given n, I will have a selection of L's, and for each of those L's, I will have a selection of m sub L's. So let's go back to the sample problem preview, and then we'll put this on the screen. And what we're going to do now is, I still have this from the previous problem. Let me get a different color out here. I have the wrong end of the pen. And so what I'm going to do is I'm going to work with n equals 2 here. And I'm going to say for L equals 0, what are the possible values of m sub L? And type it in the chat when you think you know. Oh, interesting. That's not what it's supposed to be showing you on the screen. Hold on. Let me just make sure that that's right. There we go. Yeah, I just looked over there, and it was just showing you part of the YouTube previewer window that I have. It didn't capture the correct window. That's okay. All right, so that's correct. So the values of m sub L that are possible for L equals 0 are just 0. Because if L is negative 0, which doesn't exist, or positive 0, those both collapse down to 0, and the only integer value that's possible is 0. But let's suppose that L is 1, which is right here. What are the possible values for m sub L if L is equal to 1? So negative 1 and 1 are correct, but are there any more? Because it's all integer values between those two extremes, right? So what are the values that are possible? You got 2 of them, and then the third one is kind of hiding there. There you go. That's the right answer. So negative 1, 0, and 1. We'll put positive there. Yeah, you got to include the 0, so don't forget 0. And I want to get rid of this n equals 38, because what we're going to do... Actually, let me just do it this way. Goodbye. Oh, actually, I got to tap over here to get rid of that. All right. So what we're going to do now is we're going to write out all the possible orbitals for n equals 3. All right, so let's start by writing out all the possible L values for n equals 3. So what L values are possible for n equals 3? Type them in the chat. Let me know what you got. Yeah, there you go. So 0, 1, and 2. So L equals 0, L equals 1, and L equals 2. All right, for each of those L's, what are the possible values of m sub L? So for L equals 0, what is m sub L? What's the only value it can be? 0. Very good. And then for L equals 1, what are the possible values of m sub L? Type them in the chat, write them down, whatever you want. Very good. That should be a minus. And then finally, for L equals 2, what are the possible values for m sub L? Ooh, this is a new one. Type in the values of m sub L in the chat now. And there you go. So that is how we write out all of the quantum numbers. For any given n. And then, of course, there is a fourth quantum number, but it turns out that that's just sort of a thing that we're going to tack on at the end. So what does this mean in terms of our model? So what this means is that if I only have one shape, that one shape has only one orientation. Now, if I have two shapes, which means that I have the 0 and the 1, the first shape only has one orientation, but the second shape has 3 orientations. Which means that there will be 3 versions of it. Actually, I should say the first shape instead of one shape here. For L equals 2, I also have the third shape, and that has how many orientations associated with it. Type that in the chat. How many different ways can I draw this third shape? Very good, because there are 5 values. So there are 5 orientations. And so in other words, the number of orientations is equal to the number of values for m sub L. And the take-home message that we care about for this is that the number of values for m sub L is equal to the number of orbitals. So every time you write down a number for m sub L, that is an orbital. That is a region in space where my electrons will be placed. So if there's only one orientation, I'm only going to draw one shape to place my electrons in it. If there's 3 orientations, I can draw 3 shapes. And if there's 5 orientations, I can draw 5 shapes. We're not going to draw the shapes later on. We're going to simplify this all into boxes. And we're going to just put electrons in the boxes. But each of these boxes is an orbital. And that's where my electrons will live in the ground state. So that's the importance of M sub L. M sub L is actually going to tell us which orbital we are looking at. And so that's right here. So the magnetic quantum number, not only does it determine the orientation of the orbital, but it also determines which orbital you were putting the electrons in. Now let's suppose I gave you L equals 3. What are all the possible values of M sub L? Just to review, because I already did the example, and then I forgot there was another example there. I'm just imagining you all furiously typing away on the numpad. Minus number, minus number, minus number. And there you go. So you want to have all the possible integers between -3 and 3, which would be -3, -2, -1, 0, 1, 2, 3. How many different orientations is that range, though? How many different ways could you draw the shape for L equals 3? Seven ways, and that's correct. Have you noticed the pattern here? There was one way to draw the first shape. Actually, let's go over here. We'll do that. And so for the first molecule, there was only one. Then there were 3, then there were 5. And it's only odd numbers, and it increases 2 each time to keep it odd. So if I asked you for L equals 4, yeah, there you go, 2L plus 1. Or just descending odd numbers, however you want to remember it. But if I gave you, like, say, L equals 4, and you knew, oh, well, L equals 3 has 7 orientations, L equals 4 must have 9 orientations, and L equals 5 must have 11 orientations, and so on and so forth. So it's always 2L plus 1 different possible values. All right. Let's talk a little bit more about constructing these addresses and then turning that into a diagram. And then I forget where the shapes live. Let me just scroll ahead really quickly. There's the shapes. Okay. So what I want you to do, I want you to try this example. For n equals 4, I want you to draw all the possibilities. And by draw, I mean actually just write out. So start with n equals 4 and then do how many L's are there. And then for each L, tell me all the possible values of M sub L. And then when you are done with that, count up all the orientations to tell me the total number of orbitals. Okay? And I'll give you a hint. Your number that you get for your answer will be related to n equals 4 in some way. And what I mean is that you could do some math operation to n, and you'll get the number of orbitals available. And it'll be an obvious one. It won't be like, oh, I add 19.5. Like, that's not what it'll be. It'll be a function that's on your calculator. So write out all the combinations, and we'll go over the answers in just a second. All right. Hopefully you have written out all of the orientations that you think are for n equals 4. I see some people got the right answer. Oops, I didn't do this part. So it's not the value that matters, it's the number of possible values that matters for m sub l. So what that means is that I'm going to assign numbers for the different possible values of m sub l, but I don't care if I have a -3 or a +1 or whatever. I care about the number that I wrote down. So if I wrote down 7 entries, there are 7 orientations. So let's go through all the possibilities. So for n equals 4, L could be 0, L could be 1, L could be 2, and L could be 3. How are they getting 16? We'll show that right now. So for L equals 0, M sub L can only be 0. For L equals 1, M sub L is -1, 0, or +1. And for some reason, as I got more of these, I crammed them closer together. So M sub L for L equals 2 is -2, -1, 0, 1, and 2. And then for M sub L, L equals 3, we have -3, -2, -1, 0, +1, +2, and +3. And so now what we want to do is count the number of orientations that are possible. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And since each orientation is an orbital, in n equals 4, there must be space for 16 total orbitals. Cool. There you go. And that also leads to the principle that in any orbital, in n equals whatever x is, there will be x squared total orbitals. So in n equals 1, there will be 1 orbital, because 1 squared is 1. In n equals 2, there will be 4. In n equals 20, there will be 400. I should have done a more impressive number than 20 squared. It would be like, in n equals 13, there's 169 orbitals. You'd be like, wow, Wes knows his mental math. But I caved in big 20. Yeah, see, quantum mechanics is one of those things where it's just like, what the frick is all these rules? I'm saying the F word too many times on this stream, so I'm trying to censor myself. What is with all these rules? They're all stupid and everything is awful. But in reality, yeah, the rules are stupid. But when you do this enough times, it makes sense what the logical system is that chemists are trying to get at. Because we're trying to make a mathematical model that matches what we see in reality. And that is very difficult, it turns out. For example, if you wanted to derive a mathematical model that described the shape of every tree you see, that'd be almost impossible. If you want to do that to derive the shape of every car you see, that'd be impossible because there's so many different cars out there. But you could make some simple rules like, oh, here, there's this many wheels. And for the number of wheels on the car, it affects its length, and so on and so forth. And that's what quantum mechanics is trying to do. As the atoms get bigger and you have more energy levels, the places electrons go gets more complicated. And we're just doing the best that we can to model it. And it turns out the model actually works remarkably well. We already did n equals 3, but what I want you to do is this example here. So I'm going to give you a second to look over these quantum numbers, and I want you to find any mistakes that exist within these samples. So of these sets, they are either correct or invalid for some reason. And if you find one that's invalid, sketch the reason why. Tell me what rule it broke. I'll give you a second to do that. I'm going to go fill my water, and then we'll go over the answer, and then we'll take a break. So see you in a bit. All right, have we found the invalid quantum number set? So I'm going to type in the chat how to write these quantum numbers out in just like the general sense of like how you'll see them on Canvas. So you'll have something like this, kind of like if you were writing a coordinate pair. And that L on the M sub L should be a subscript, but I can't actually do that. So like, for example, if you did n equals 2, L equals 1, M sub L equals -1, you do something like that. So type in the one that you think is wrong using the coordinate notation. And as soon as I said that, everybody already agreed on which one's wrong. And it is that one. And the reason for this is for a specific reason. It has to break one of the rules. What rule did it break? So it is this one. But what part of it's wrong? Knowing that's wrong is, or knowing which part of it is wrong is just as important as identifying that the whole thing is wrong. Can n be larger than 3? What possible values are there for n? Yeah, you can go all the way up to infinity, so you can pick any n you want. Earlier we had like an n equals 38 example, so you can do that. You can have a really big n. But L restricts which value of M sub L you have, so this doesn't work because M sub L has to be greater than or equal to negative L, and it has to be less than or equal to positive L. So if L is 1, M sub L could only be -1, 0, or 1. And it can't be -2. So this one is invalid because we have an inappropriate value of M sub L. That doesn't exist for that orbital. Alright, so now that we know how to write the quantum numbers out, we're going to have to translate these quantum numbers into shapes. And so what we're going to end up doing later on is we're going to see stuff like this. Here's our quantum number for n equals 2, L equals 0, and M sub L. We're going to start writing these orbitals by taking them from quantum number coordinates and putting them into things like this. So we're going to translate them into letter codes based on just the n and the l. In fact, M sub L here isn't super useful to us, other than to just know how many of them we have. So when we come back, we're going to talk about shapes of orbitals, how we translate these into the letter codes for the orbitals, so S, P, D, and F. And then finally, we're going to construct the electron diagram, putting all of this information together, And by the time that you are done with today's lecture, you will have seen that electron diagram so many times that you'll basically have it memorized and know how to construct it by heart. So I'm going to put the title card back up. It is time for a break. I do need a timer. Did I put live split on my desktop? I can't actually see my desktop because of PowerPoint here. So let me do that. And I'll start the timer. We'll start our break. And I'll see you in 10 minutes. Have a good break. Sigh. One of these days I'll get it. Alright, I hope everybody had a good break. We're going to get back to... Let me get rid of these again. Boop, boop, boop. Let's get back to our discussion on atomic orbitals and their shapes. I'm just imagining everybody racing back to their seats. Oh, will he stop it right on 10? You know, I only have like 10 more attempts at that, right? Because, well, we only have... Yeah, 10 more tries. Well, 9 more tries, I guess, but that's okay. Alright. So, when we describe L within an orbital, we are actually describing its shape. And the shape is going to depend on what the value of L is, but also on what value N is. M sub L won't change the shape, but it'll change the direction it's pointed based on its value. And I should say that that's true for S and P orbitals. For D orbitals, it kind of falls apart a little bit. And for F orbitals, everything falls apart a bit. So let's look at L equals 0. So this is going to be our S orbital. So if I have N equals 1 and L equals 0, that would be a 1s orbital. And that orbital is just a simple sphere. Now, our electrons could be anywhere within that sphere. They could technically be outside of the sphere, but the sphere represents the probability of where I will find the electrons most of the time. And so most of the time, and when I say most, I mean like 99% of the time, the electrons will be within this sphere. Now, if I go to 2s, which is n equals 2, L equals 0, it's just a bigger sphere. And if I have n equals 3, it's an even bigger sphere. But there's a catch to this. So the sphere is not just like a ball that's getting bigger and bigger and bigger. What we're actually doing is we are layering these spheres on top of each other. So in the 2s orbital, there's a second sphere inside. And in the 3s orbital, there's the 2s orbital stacked on top. And those are supposed to be circles, but I'm bad at drawing circles. You could kind of think of this as like a cake. So if the 1s orbital is a cake, then I built this ball of cake and then I frosted the outside. But the n equals 2 layer would have a cake for the 1s, and then it would have the frosting, and then it would have the layer for 2s, and then I would frost the outer layer. So it'd be like a 2-layer cake. And then for 3s, it'd be a 3-layer cake. Now, why do we care about that? Because the frosting in these cakes is actually going to be very important. Remember how we talked about nodes? And how that, for like a wave, nodes existed, and that the nodes represented places where the energy was 0? Well, because electrons behave like waves, in the orbital, the electrons are going to basically be wave-like. And what that means is that if we put electrons at higher energy states, such as, say, n equals 2, nodes start to appear. And those nodes represent areas that the electrons can never be. So here's my n equals 2 sphere for the 2s orbital, and you'll see that this right here that I'm going to draw in red, this is the thick part of the 1s orbital that is darkened. And then on the outside we have... Oops, I apparently selected something. On the outside we have a high probability of finding our electron as well. But then there's this like pale region in the middle. And that pale region represents the node. That's the frosting of our cake ball thing that I made up. And because the electrons are behaving like waves, at the node, the value of the wave is 0, right? So the value of the electron is 0, and thus the probability of finding the electron is 0. So you will never find an electron at the nodes. So what that means is that the orbital diagrams for spheres, for 1s, 2s, etc., they get more complicated as you increase the energy level. And remember, there will always be n-1 nodes. So for an n equals 1 orbital, you would have 1 minus 1, or 0 nodes. For n equals 2, you would have n-1, or 1 node. And there it is. Now, those nodes that you see here are radial nodes. Remember how we had radial nodes when I showed you that diagram of the two-dimensional wave? Which means that at some radius away, my node exists. So if this was my 2s orbital, my electrons can't be this specific distance r from the nucleus, because that's where the radial node is. What about angular nodes? Well, the angular nodes are going to come up when we get to the next wave function, which is the p orbital. All right. Here's my 3s orbital. You can see the two nodes drawn on that. The diagram at the bottom is just what the orbital would look like if I made it one-dimensional. So this is just like a slice of it. And this is how likely I am to find the electron at this given spot. But you'll notice that the probability becomes 0 at very specific spots. And those spots are the nodes. So I will never find the electron in those spots. And again, for any s orbital, there are always n-1 radial nodes, because there has to be n-1 total nodes. And for an s orbital, there can't be any angular nodes. And we'll talk about why that is in a second. I believe it's on the next slide. Now, for any orbital, so whether it's s, p, d, f, whatever, there are always going to be n-l-1 radial nodes. And I realize that this is obnoxious here. So this is an L, but these other ones are 1s, the number 1. And so what that means is that p orbitals can have radial nodes too, because radial nodes and angular nodes can coexist. We saw that on the video with the sand that was spilled on the vibrating plate. The frequency plate, I guess we'll call it. And we're going to see that when we get to the p orbitals in just a second. Alright, so here's what a p orbital looks like. The p orbital looks kind of like a little dumbbell or a bow tie. And you'll notice that it kind of pinches in the middle. And so it's like somebody took this and went boop, or it was a balloon and they twisted it around the center here. Now, it turns out that this is the planar node. And I'm going to try and draw that in yellow here. So if I draw this box like this, and this one actually goes behind here, and then I fill in this plane like this, and the reason I chose yellow is because it would be a little fainter, but I'm not super happy with my color choice now. So you'll notice that along that XY plane there, and let me choose a darker yellow. Can I highlight it? Does this help? It helps a little bit. Along the XY plane, my electrons will never be found in this p orbital. Over here on this second one, I could do the same thing, except that I have a different plane. So if I go like this, and I fill in this plane right here, my electrons will never be found on this plane. Now you're noticing that I'm coloring over parts of the orbitals, and that's because this part of the orbital is behind. Because we're in 3D now. But nowhere along this YZ plane will my electrons be found. And then I could do the same thing for the third orbital, where it'd be along the XZ plane. Now, This is the result of our mathematical equation for where our electrons cannot be at a given angle around the origin. And so these are our angular nodes in 3D. Now, in 3 dimensions, an angular node becomes a 2-dimensional surface. Because in 2 dimensions, our angular node was a 1-dimensional line. And so what we end up calling them now is, instead of calling them angular nodes, we're going to call them planar nodes. And so the planar nodes are going to be the result of the equations that are used to make these shapes, which, again, you don't need to really know the math behind that, but you do need to know that if you see like a pinched area in your picture, no electrons will ever be in that pinch, because that's part of the planar node. And that's why these shapes do this. And again, because we created this m sub l here, so if I say that n equals 2, l equals 1 is the p orbital. For n equals 1, m sub l could be -1, 0, and +1. And I can assign these numbers however I want to. So this one might be -1, this one might be 0, and this one might be +1. And in reality, it doesn't matter what numbers I give them, because I could rotate these axes in 3D however I want to. So the one facing up and down could be +1 if I rotated everything 90 degrees in some direction. So it's all arbitrary. But what we care about is the fact that we got 3 numbers out of this, so we have 3 different orientations of our shape. Next, I'll show you the D-Orbitals. Oh, I guess I'll show you. We already talked about planar nodes. Yeah, here's the D-Orbitals. This is why we don't really care about talking about D-Orbitals, because they get more ridiculous. So D-Orbitals are beyond the scope of this class. You're not going to have to memorize these shapes. You should recognize the gist of what a d-orbital is. Like, oh, it looks funky, it's probably a d-orbital. And then I don't know what this, like, p orbital trapped in a donut thing is. Like, I don't know what's going on here. And I studied this stuff for years. This is just why the math, how the math falls out. So shape is determined by L, and the orientation is determined by m sub L. Yep, that's right. N is the energy level, and so as the energy level increases, these shapes get bigger. So, like, if I wanted to draw a 3p orbital, which you're going to draw in a second, you're going to draw it like a 2p orbital and then add a radial node to it. Here's the f orbitals. Again, these get ridiculous to an even further extreme. And you don't need to memorize these because they're dumb. In fact, f orbitals are not super useful. And I say that having studied them extensively. Alright, so what I want you to do is I want you to try and draw a 5s orbital with the correct number of nodes. Draw it on like a 3D axis. And then I want you to try and do that with a 5p orbital. And draw it along any orientation you want. But I want you to put in the correct number of both radial nodes and planar nodes for each one. Okay. Alright, so go ahead and do that, and we'll be back in just a second to go over the answer. Sorry, I tried to click on something. It didn't work. I didn't mean to do that. All right, hopefully you have drawn your shape. I'm just preparing something for the next slide that we're going to do in a second. Actually, let's do it this way. Okay, I don't want this to appear yet, but I do want it, like... Okay, cool. All right, so let me go to the sample preview. And let's draw a 5s orbital. So a 1s orbital is a sphere. So a 5s orbital, which is also s, should have just as just the same shape, so a sphere. Oh, that was starting out really good, and then I messed it up at the end. And it should be much larger than a 1s sphere. And so a 5s orbital will have 4 radial nodes. So I need to go 1, 2, 3, and I can just put them wherever I want to here. So it looks something like that. That's the best I could probably do. Now it's important to notice, that this is a 5s orbital. So there aren't 25 orbitals for 5s. There are 25 orbitals in n equals 5, of which 5s is one of them. And so you could draw the 5p orbitals, and the 5d orbitals, and the 5f orbitals, and the 5g orbitals. And when you add all those numbers together, you'd have 1 5s, 3 5p, 5 5d, and so on and so forth. And you'd eventually end up with 25. All right, so that's what 5s looks like. And then if I wanted to draw 5p, well, 5p is a dumbbell. And so I have a planar node, so that's what's going to be right there. So I have one node taken care of. Not one node, one node. And so if I have one of the nodes accounted for, I should have 4 total nodes because there are n minus 1 nodes, right? So 1 is planar. And the other 3 must be radial. Because that will be my 4 total nodes. So I got to do, here's a radial node. So 1, 2, 3. That's the best that I can do. It looks terrible. Now, in reality, the nodes are not going to be super important. It's just nice to know that they exist. But for our purposes, we're going to be working with orbitals like n equals 1 and 2 anyway, and so we aren't going to be really drawing any nodes other than the planar node. So that's going to be the most important node, is the planar node. And that's really obvious to draw. You just pinch the p orbital in the middle. And that's all we're going to do for s and p orbitals. All right, before we continue to the next section, which talks about phases and stuff of orbitals, and we're almost done with this. We're going to construct the orbital diagram in just a second. I do want to briefly show you what the formulas for the equations that were used to make these orbitals are. And so if you like math, then this will look very good to you. So hold on, let me make sure I have the right window capture here. Yeah, there it is. So should be this. Yeah, it's terrible. And I hope that I unmuted the music. Oh, I didn't. Oh, I ruined it. So you're probably just like, why is he scrolling everything around? Because I had this playing here. And it's muted. God damn it. Man, I'm the worst at trying to pull off jokes here. You're just like, why is he shaking the screen? There we go. All right, you should have been able to hear it that time. damn it, I set that up for like 5 minutes and nothing worked. But anyway, there's the equations that are used to make these orbitals. And you can see the N, L, and M sub L values up here. M is only abbreviated for whatever reason. I don't know why they called it just M. But, like, no. Just no. It's gross. But what I can say about these equations is that because they are equations, and they're functions of r, which is the radius, and a sub 0 is a constant, if you plug these numbers in and do the integration and you get a three-dimensional result, those results will have positive and negative values because they're math, right? All math on the real number line could be either above 0 or below 0. And so when I plot these shapes in 3 dimensions, what ends up happening is that those solutions actually have results to themselves that depend on the sign. And so what I showed you was part of the Schrodinger equation. So it's the mathematical relationship between how orbitals are shaped based on calculus. And again, we don't ever want to see that again because it's gross. But because electron orbitals are treated as waves, because the electrons are behaving as waves, and the waves are modeled with those equations that you saw, sometimes there's positive components to the equation, and sometimes there's negative components. And so this is really only going to be super important to you in organic chemistry when phase becomes important. That was supposed to be the word negative, and then I tried to write a minus sign, and then I got confused. And so these are just the positive and negative parts of the equation, because they can be above or below 0. And so what that means is when I draw phases in my orbitals, my equations will either have a positive solution when I represent them as a shape, or negative. And remember, these are in terms of the math. So positive solution, that just looks stupid. Hold on. And what this is not referring to is charge, okay? Because I realize that we use positive and negative for charge as well as number lines, and that is an unfortunate conundrum that chemists face. So when I say, oh, this is a positive region and a negative region, I don't mean charge, because electrons are always going to live in these orbitals, so it's always going to have a negative charge. But the math for it does have a positive component and a negative component in terms of the number. And what that means is that later on in chapter 5? In chapter 5, we're actually going to take these shapes and we're going to add them together. We're going to do shape math. Where's that dun 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 sound? Do I still have it? No, I don't. I turned it off. But we're going to add these equations together, and we're going to use the result of that to make combined orbitals in which things live. That is if we have time. I don't know if we're going to have time to go over molecular orbital theory. But that is a thing that you can do, and that is mostly done in organic chemistry. So yeah, it's just important to remember that when you get to Chem 261 or 262, and either Samita or Steve or Maxie or whoever you have then is like, hey, did you learn about phases? You could be like, yeah, I sort of remember something about that. Because orbitals will be important then. And yeah, so that's all we really care about for phases. Let's talk about this last quantum number that I've been holding close to my chest. So there is one final quantum number in the set of 4 quantum numbers. And that is called the spin quantum number. And what the spin quantum number refers to is how electrons behave when they spin. And so if I have an entity that has a charge, and that entity rotates in some direction. What ends up happening is that I create a magnetic field. This is just a consequence of charge. And that magnetic field has orientation to it, north or south. Now, this is going to depend on the direction that the entity is rotating. If it is rotating in the other direction, then the pole that is generated is opposite. And you can see this on the diagram below, but I'm just drawing it so that you can see it in action. Now, if I have these two entities next to each other, these two electrons, then what's going to end up happening is I have a negative. I need another color here. Hold on. I have a negative and a negative that are going to repel each other. And so these two electrons will push each other apart due to their charge. But what happens to their magnetic component? Well, there's an attraction there. And so what that means is that even though the electrons repel each other because they have a negative charge, they're very tsundere about it. I don't know how to pronounce the word. It's the Japanese, like, that the person that, like, doesn't want to talk to anybody and calls them baka, but secretly likes them. I know how to spell it, I just don't know how to pronounce it. Anyway, that's what electrons do. Electrons are very tsundere. The magnetic component provides a weak attraction, and that is just enough to allow us to pair two electrons together into an orbital, but only if they have opposite spin. The values that we assign for spin are just arbitrary as well, so it's either positive 1/2 or negative 1/2. You can assign the positive 1/2 to be up or down. It doesn't really matter. The convention is up. So whenever I draw an up arrow for our electron, it will be assumed that it has spin positive 1/2. And then spin negative 1/2 is just, it's pointed in the other direction. And as long as I have oppositely spinned electrons, I can put them in the same orbital. So whatever that region of space is, whether it's the s orbital because it's a sphere, whether it's the p orbital because it's a bow tie, whatever, I can put my two electrons in there as long as they are oppositely spun. Okay. Now, spin is a fundamental property. All electrons have spin. So you will never see a spin 0 electron because everything just spins around. BO is an unpleasant odor that is emitted by... No, I'm just kidding. BO is the strength of a magnetic field. So B is the variable used for magnetism in physics. And so 0 is just, I think, the elementary strength of the magnetic field emitted by an electron. You do not need to know that. You do need to know that electrons have a magnetic pole, and that is their spin. Or that is the result of their spin, I should say. But you don't need to know what B is. We're not going to do magnetism until, like, Physics 241 or something like that. So now we have all four quantum numbers for a given electron. We have n, which is the principal quantum number. That's the level that the electrons will live on. We have L, which is the shape of the orbital that they live in. M sub L is which specific direction they live in. And then M sub S is the electron that lives in that orbital, either spin up or spin down. Now, because spins will pair together to fit in an orbital, if they are opposite, the conclusion that we would draw is that if you have two electrons that have the same spin, they would repel each other further. If you put two magnets against each other and you put the same pole pointed at the same pole, they repel each other very strongly. And so the requirement for two electrons to pair in any orbital is that they cannot have the same spin. Notice that I have not said they must have opposite spin. And the reason for this is because the possibility of other spins does exist. We just have never observed them. But what we know is true is that you can't have two electrons that are both spin up. If for some reason we discovered an exotic state of matter that had like spin 0, for example, perhaps spin 0 could coexist with these other two. And then we'd have to change the Pauli exclusion principle. But the Pauli exclusion principle is very specific with its language. You can't put the same spin in the same orbital. Now, that means that I can actually open a bunch of nefarious questions for you, which might be along the lines of, what if there were 4 spins? What would an orbital look like? And so on and so forth. So be very mindful of the definition of this question, because it will come up later on the Chapter 3 quiz. Alright, so earlier on we determined all of the orbitals in n equals 4, and we called them 4s, 4p, 4 whatever. I want you to first go back to those notes and find where you wrote down all the orbitals in n equals 4, n, l, m sub l, m sub s, or whatever. And then I want you to tell me how many electrons can be contained in the entire shell, n equals 4, if for every orbital, and an orbital is an m sub l, you could put 2 electrons. Okay. And then I want you to try and do the same thing for shell 2 and shell 5. And then what I'm going to do is I'm going to draw the diagram out for you. And that diagram is going to look sort of like... Let me find the picture here. It'll start looking like this. Okay? So you've probably looked through your book and seen this. We're going to draw this diagram after we do the example. And it didn't go backwards. There we go. Alright, so count the number of electrons that go in each of these shells. Shell 4, shell 2, shell 5. I'll get back to that in just a second. We'll draw the answer. All right, how are we doing? So hopefully you have counted the total number of electrons in n equals 4. We're going to do n equals 4 on the preview page here. I just wanted to show this again before it's gone forever because my drawing is terrible. So just to review how we did this before, so n equals 4. And I'm going to arrange this more vertical this time. So I'm going to go L equals 0, L equals 1, L equals 2. I'm going to scroll down to do this, but that's okay. And so for a given L, we can calculate m sub L. So for n equals 4, L equals 0, m sub L is also 0. For n equals 4, L equals 1, m sub L will be -1, 0, or 1. For L equals 2, m sub L will be -2, -1, 0, +1, +2. I didn't put a positive up here, but that's okay. And then for L equals 3, m sub L will be -3, -2, -1, 0, +1, +2, and +3. And now what we're going to do is we're going to count orbitals, because remember, every time I have an m sub L entry, that is an orbital. So I have 1, 2, 3, 4 orbitals. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 orbitals for n equals 4. And that makes sense because n squared is 16, where n is 4. And now if we use the Pauli exclusion principle, we could say the Pauli exclusion principle means that I can have an electron that is spin up, and I can have an electron that is spin down in an orbital. So, in other words, we can have 2 electrons per orbital. And this notation that you see right here, where I have this like half arrow pointing up and down, so this is my spin down electron. In other words, m sub s is -1/2. And this is my spin up electron. And so since I can pair 2 electrons per orbital, I must have 16 orbitals times 2 electrons per orbital. I misspelled orbital. So 2 electrons per orbital equals 32 electrons, and n equals 4. Now, we haven't gotten to this yet, but if you look at a periodic table, if there are 32 possible electrons in n equals 4, what that means is that you should be able to find a row where there are 32 elements in it. And so when we actually start talking about how the electronic structure corresponds with elements that have certain numbers of electrons, what you'll find is that if you look at some of these rows, if you were to slide the lanthanides and actinides up into where they go and you count all the way across, you actually get 32. And so all of this information is all connected in some way. And we'll talk about that more on Thursday. But the last thing that I want to talk about before we go is I want to show how we're going to start constructing all of this information to synthesize into an electron diagram. So in order to do that, I need to clear the screen. And so the way that this is going to work is that we need to write out every possible combination for all quantum numbers ever to make our diagram. And the way that this is going to work is we'll just start at n equals 1. What are the possible values of L? Well, there's only one. What are the possible values of M sub L? There's only one. So this orbital, based on this information right here, would be a 1s orbital. And what I end up doing is in my diagram, I do this. I'm going to put a box, one box per orientation. And then I can do that for n equals 2. So n equals 2 would have L equals 0. Oops, hold on, let me do it this way. So because I have n equals 2, L equals 0, that would be 2s. But I also have available L equals 1, which would be M sub L equals -1, 0, or +1. That's 3 orientations, and this would be 2p. That was a really bad straight line. Good job, me. Very good. And then we can do the same thing for n equals 3. So n equals 3, L equals 0, M sub L is 0, 3 L0, which is S, 3s. For n equals 3, L equals 1, M sub L equals -1, 0, +1. That would be 3p. And then finally, L equals 2. M sub L is -2, -1, 0, +1, +2. For L equals 2, the letter was D. And how many boxes do I write for that one? So how big is 3D going to be? How many boxes should I put down? And 5 is right. Very good. And this keeps going, so I could do 4s, 4p, 4d, 4f, etc., and so on and so forth. There is a little bit more to this, but this is what the basic diagram is going to look like before we consider stuff like splitting. Now, you do need to memorize it, but in a way you don't, because you're at home. This is all just going to be stuff that you just reference, right? Imagine if you were in class and you had to memorize this, but I would make you if you were in class. Now, lastly, where do our electrons live in all of this? Well, because electrons can be spin up or spin down, and I can pair them in here, I would just pick the lowest energy that's closest to the nucleus. So here's where my first electron would go. This is what hydrogen would look like. It has 1 electron, so it goes in the spot. Helium has 2 electrons. Lithium has 3 electrons. Beryllium is 4, and so on and so forth. And we just keep adding electrons as we add them to our orbitals to fill up the structure. Now, later on, I'm going to talk about how splitting works. So 2s and 2p are actually not the same energy. 2p is actually going to be a little higher in energy. 3p is going to be higher in energy, and 3d is going to be higher still. And we'll talk about why that happens very briefly. Your textbook doesn't really go into it, unfortunately. But I will talk about it. But this is how we can start to construct the orbital diagram based on all these quantum numbers that we've used. And once we get to this point where we're using this diagram over here, I don't know if it's clicked on this. Oh, you can see my cursor. Once we get to the point where you start using this diagram, the quantum numbers sort of just go away, which is nice because what do we want to deal with all these quantum numbers for? And the answer is, well, we really don't. We want to deal with pictures so that we can represent this abstractly instead of from a completely mathematical perspective. So please review parts of Chapter 3 where it starts talking about and showing those electron diagrams, because that's what we're going to start doing next time when we come back on Thursday. which is the next section, electron configurations. Look at that. We're only halfway done with Chapter 3. We may finish Chapter 3 by the end of next week, which would actually be really great, because Chapter 4 is pretty long, but Chapter 5 is not. So we will continue on Thursday with our discussion of electron configurations. We're going to put all of this stuff together. You'll need a periodic table, and everything will just start to fall into place. Just a reminder again, there is no lab lecture tomorrow. I will not be streaming. You may still email me questions if you have them, and I'll answer them over email. But I'm just not going to have a live stream. I'm going to be working on getting that lab prepped for next week, and then if I run out of things to do, I'll do the next one after that. Thanks for watching. Put the title card back up, and I will see you on Thursday. Have a good one, everybody.